Okay, let me start this discussion. Working of PN junction. Working of PN junction can be understood once by forward biasing it or one by reversal. Because in PN junction, if you look clearly, one terminal and the terminal number two. So this is terminal number one, and there is only two terminals are possible. If you have two terminal, either you can apply higher voltage to this terminal or lower. Only this is the two possibility you have, and that is why only two modes are there in PN junction. So now let me take another very important discussion. Actually, what I have personally observed, people will ask to draw the IV characteristic of a PN junction under both forward bias and reverse bias. Actually, we are not confirm, or we are have lots of confusion what this current I means. From where this current I is flowing, we don't know. Most of the student, my student, don't know how this I is coming from, which I magnitude of I is depend upon what factor. Okay, there are so many electrons are there. Whether these electrons are moving in this region contributes this current, or in this region contribute this current, or at the junction these electrons or charge carriers are moving, so this is contributing in this one. So we will be seeing those things. Okay, so now first of all I want to make one more clear. By definition, if you see in most of the books or in most of the YouTube videos or anywhere, you are going to say that when we want to forward bias this PN junction, then apply positive voltage to the P type and the negative voltage to N type. Please don't remember those things. From now onwards, remember that if you want to forward bias your PN junction, definitely then you have to apply higher voltage to the P type and lower voltage to the N type. Sir, what is the difference between them? P for positive we can apply, here we can apply negative. Because I am saying that, suppose let me take another cases for example. Now suppose we can take 5 volt here and the 0 volt here. You can say that yes, positive voltage is applied to P type and 0 voltage is applied to negative, it is forward bias. But there are so many cases will come. For example, suppose this is minus 5 volt and this is minus 10 volt. So now tell me whether your PN junction is forward bias or reverse bias. By your definition, what is written in your book or anywhere on YouTube video, for it is will be forward bias only when you apply P type with a positive voltage. See, I have applied negative, and here I have applied minus 10. But if you go by this definition now, this PN junction is forward bias because this is minus 5 and this is minus 10, which is higher. So minus 5 is higher as compared to minus 10. So now this junction is forward bias. Some cases you will see minus 2 volt, minus 8 volt, then also it is forward bias. 2 volt and minus 3 volt, again this is higher voltage as compared to this one. So all these cases you are not going to remember. Yes, this higher means higher, whether it is positive, whether it is negative, I am not going to bother about that. We know if you want to forward bias your junction, P side must have higher voltage as compared to the N type terminal voltage, and now you can say that this is basically your forward bias. Clear? Now this is clear, but now I am going to tell you, while drawing the IV characteristics of your PN junction under forward bias, please remember that whatever current is flowing or whatever current is drawing in this diagram is basically the current or the charge carrier movement at the junction. What is going on at the junction, this will be the current which we are going to draw in the IV characteristics. Now for example, that means what you want to say, sir, suppose this is an N type region, sir, and this is our P type region. If electrons are moving in this direction in N type region, and if holes are moving in this direction, because of hole the direction of the current will be I, because of the electron the direction of the current I, and in at the junction we know there are so many carriers. Now at the junction, suppose the electrons are going in this direction as well as holes are coming in this direction. So now we can say that here also some current will flow. This current is I. Now which I is basically drawn in the IV characteristics? Remember that in PN junction or any other devices which is comprises of junction, we are looking to the charge carrier which are crossing the junction. Those carrier which are crossing the junction is basically drawn in the IV characteristics. So this I is basically the current due to charge carrier movement at the junction, not in the N region, not in the P region. If some electrons are coming in the N side region and these electron haven't crossed those junction, that means this electron is not going to have any impact on the current. In the current, those charge will not be included. Only those electron which is moving from the N side region and cross the junction will be responsible for the current, and those current is drawn in the IV characteristics. I will show you what I am saying, why I am saying this. Please look in this picture. So now for this case, forward biasing this, I am drawing this. This will be 5 volt and this will be, or we can say that this is 0 volt, or we can say that minus 5 volt. So now you have applied these voltages at the terminal, sir. Now this PN junction is forward bias, and if this forward junction is forward bias, what will happen? Because of this 5 volts, sir, what will happen? This is positive and the holes are also positive. So these holes experience some force and they will try to move in this direction because of this. Similarly, there are electrons and this is positive charge carrier. These electron will be attracted also. Now the electron movement will be in this direction. Similarly, this is minus 5 volt. So minus 5 will attract the holes and this minus 5 will repel this electron. So now this picture will be coming if you forward bias the PN junction. The hole will try to move in this direction and these electrons will try to move in this direction. But look at this. So these are the minority carriers, minority electrons in the N region. They will experience one force. Now this electron will be moving in this direction, and now this electron may come outside, and now this is the electron's movement. But these holes will go in this direction and this electron from there also come, and this will be joining by this electron, and similarly the electrons will come here. So that means these electrons are not crossing the junction. That means whatever I you will draw there now, these electron will never contribute in that I. Whatever I you are going to draw is basically because of those electrons which are crossing the junction. Similarly, these holes are attracted by this, but remember that these holes are the concept only for the semiconductor material. There is no physical meaning of holes outside the semiconductor material. So this is basically a conducting wire. In conducting wire, no concept was there for hole. So suppose we have to stop, holes may come to this point only. So these holes, after getting from this, they will accumulate in this picture. Like electrons are going to this positive terminals, electron holes cannot go in this one because there is no concept of holes in the semiconductor or conductor material. So these holes are basically a concept of semiconductor material. So they are basically in between the semiconductor material. So now what will happen? There are so many holes are there, and these electrons will go, and we know this is battery. So electron will go, and similarly this electron will go there, and they will recombine here, and this will be there. So now if you look at the junctions, or what happens from the N region, the electrons are coming in this direction. From the hole, this is going to this direction. So now if we look at the current direction, sir, so the current will be in the direction of hole. So this is the current I, So if we assume this direction current as a positive current, so this direction I am assuming from for this to is positive. So the holes are moving in this direction, the direction of the current will be in this direction. If the electrons are moving in this direction, the current will be in the opposite direction. So this is the direction of the current, and we have assumed this direction to be positive. Now if we have assumed this direction will be negative. Okay, this is just an assumption. So now tell me, all those electrons, tell me these junction, which electrons are crossing the junction? Majority or minority? Sir, whatever electron or holes are crossing the junction, they are majority. Majority electron concentrations are crossing the junction, and majority hole concentration are crossing the junction. So these current I is because of the majority carrier concentration in N region and the P region, and because of this movement some current will flow, and that is basically drawn on the voltage. So if the voltages are very small, if voltages are very small, few holes and few electron will come together. But as soon as voltage goes on increasing, all the holes and all the whole electron will come. So at the junction, initially if the voltages are very small, only few electron will take part, and because of this only small magnitude of current will flow. So now let me take this. Now initially the voltages are zero, so the current will also be zero. As soon as we increase the voltages, these electron holes will go their side and electron will go that side, but this internal electric field will create an hindrance, and this hindrance will be something. So if this is 0.2, it is not allowed, 0.3 and somehow, so that means few, up to few voltages no current is allowed. But as soon as the voltages become greater than this voltage which is created by this electric field is, now these holes are allowed to this one, electrons are allowed to this one, and that is called cut-in voltage. So this is called cut-in voltage. After cut-in voltage, the holes are allowed to move in this one and electrons are allowed to in this direction, and then some current will start flowing, and this current will goes on increasing as it goes on increasing the voltage, and this is called the forward bias IV characteristics. And this current is the current at the junction. So at the junction, this current is the, whatever current we are drawing is basically the current at the junction. Whatever charge carrier are crossing the junction is basically we have drawn on this one. So in the forward bias IV characteristics, this is the characteristics after cut-in voltage, the current will increase exponentially. But below the cut-in voltage, no charge carrier will be or no current will be there, because of this internal electric field, there will be development of some internal built-in potential, and this built-in potential will be overcome, so that this will allow to this one, and this is created because of the forward bias. So if you apply the forward bias, you have to increase the forward bias more than the built-in potential. As soon as the built-in potential it crosses the built-in potential, the current will start flowing, and slowly it will increase, because if you apply less voltage, less holes will cross this and less electron will come to this one, and if you increase the voltage, more holes will go to this side and more electron will go there, and so on, this current will goes on increasing, and this is the working of PN junction under forward bias. Now we are going to see the working of, now one more thing is that this current does not involve any minority carrier current. This minority carrier current is not paying any attention, first thing. And the second thing is that we have assumed this direction, that is from left to right, as a positive, but because the holes are moving in this direction, see, the holes are moving in this direction, the electrons are moving in this direction, and because of this current is in this direction. So this is the current direction, and we have assumed this. Now see, this I is positive. Okay, now I'm going to show you the working of PN junction under reverse bias. Under reverse bias, it will play a very crucial role. There are two concepts I'm going to tell you. Please see that. So now coming to the discussion of reverse bias. So this is the discussion of reverse bias. If you look at the reverse bias, in order to reverse bias the p-n junction, we have to apply the positive, or we can say that higher voltage to n type and the lower voltage to p type. At this scenario, this is basically 0 voltage is applied to the p type and the 5 voltage is applied to the n type, as we know, as the nodal analysis we all know. So this is the case. So in this case, higher voltage is applied to n, lower voltage are applied to p, and this is basically in reverse bias. What exactly happens in reverse bias? Look at this picture. So this is positive voltage. So all these electrons will get attracted. Please remember carefully. These electrons will get collected, attracted. Now these electron will come out of this surface. So now these electrons are coming, and these electrons are coming to this positive terminal. Now similarly, this is negative terminal, or we can say zero terminal. All the holes are attracted, but the whole concept is only valid to the semiconductor material. This whole concept will not go outside this concept. So all the holes are basically collected at the junction or the near the surface. See, all the holes in the p regions are moving in this direction. All the electrons, all the majority carriers are moving in this direction. But tell me, is there any movement at the junction? At the junction, there are so many electrons here, so many holes are there, so many holes are there. But all the holes are moving in this, all the electrons are moving in that direction, all the holes are moving in this direction. But at the junction, no charge is crossing. So this current, what I told you, this current is basically because of the charge carrier movement at the junction. So ideally there is no current at this junction. So now when you apply this scenario, what happen? All the electron will come that side, all the hole will be contracted this side, but at the junction there will be no movement of charge, and because of this the current is zero. Now but look at this picture, sir. But this is positive, sir. There are two holes are there. That means two holes are there. Those holes are getting forced into this direction. Similarly, these two minority carriers are getting attracted to this one. So now if you look at this, only in this scenario those minority carriers are getting crossed in this direction, and those minority holes in the end region are getting moved in this direction. So if you look at this, there are majority carriers are moving in this, not crossing the junction, but minority means very less number of carriers are crossing the junction, and because of this the direction of the current will be this one, because this is holes are moving in this direction. So the direction of the current is basically this one. Electrons are moving in this direction, so the current of direction will be this one. Now tell me, this is the direction of the current. This I will be small or large? Definitely it is small, because this I is basically because of the few minority carriers, few electrons and few holes. So these are called the minority carrier, and that is why it is denoted by a term I naught. And this is called minority carrier concentration current, and the magnitude of this current is very small. Now, if we want to draw this on this picture IV curve, remember in the forward bias we have assumed this direction to be positive one. But if you look into this picture, what is the direction of I naught? The I naught direction is in this direction. So if we have assumed I as a positive current in this direction, so this current is nothing but negative. And that is why, that means ideally no current is zero at 0 volt, but when we apply some voltage, definitely some current will flow, and this value of this current is I naught, that is minus I naught. So some currents are flowing, that is some currents are flowing, and if you increase the voltages also, nothing will happen, because these charge carrier or minority charge carriers are very limited. If you increase the voltages also, what happens? 2, 3, 4, 5, or very less number of electrons are crossing? No, it will not have any impact on the current magnitude. But earlier what is happening on, for less voltages, few electrons are coming, few electrons are coming, because millions of holes are there, millions of electrons are there, but here only few electrons and holes are there, and they are crossing the junction. The magnitude is always remains constant only, and this is called the minority carrier, and that is why it has been drawn like this. That means whatever you increase the voltages, the current is going to be constant, and that current will be equal to the I naught, but the magnitude of I naught will be negative, because you have assumed this direction as a positive. So that is why we see in the IV characteristics, this type of characteristic we have to draw. Now, but when we go on increasing the voltage, large voltage, what will happen? These electrons will absorb huge amount of energy. Now our concept, whichever we have seen in our video number 1, that concept will be useful. These electron at very high voltage will absorb more amount of energy, and it will start moving very fast. When these electrons are moving slowly, although there are on the back of the mind there are so many covalent bond, they are moving slowly and they are skipping this covalent bond and they are reaching, but this electron must have large amount of energy. Now this electron will penetrate with a speed of bullet or more. What will happen while moving? This electron now is capable of breaking covalent bond, which is not drawn in the figure, but in our mind it is there. While moving, this electron may or might break so many electrons or covalent bond. So while breaking those covalent bond, for example, tell me, if in this electron while moving break one covalent bond, what will happen? Two electron and two hole will be generated. So suppose these two holes are generated and these holes are moving in this direction, again these two electron will again move in this direction. Now tell me, these two electrons were moving and they will generate four electrons. Let me take it. One electron, suppose these two electrons are present. When they are moving, they have collided with a covalent bond, and with the collision of this covalent bond, what they have done? They have generated two more electron, and here also these two electron. So these two electron have generated four electron. Further, these four electron will generate again these two and these two. They have generated eight electron, four electron, two electron, this likewise. So this will generate electron like this one, and this process is called avalanche process. And because of this large number of electrons generated due to breaking of covalent bond, because of this sufficient amount of energy is gained by this electron while moving, it break so many covalent bond, and because of this type of process occur, and this is called avalanche breakdown. Now earlier the current is not changing, but if this process will occur, what will happen? Number of electron concentration will go on increasing, and here also because of the moment, some of the covalent bond again breaking there, so number of hole concentration are getting increased. So hole concentration are getting increased, electron concentration are getting increased, and they are crossing the junction, and because of this, what will happen? The current will again increase, but in the same direction of I naught. So at sufficiently large voltage, the current start increasing and increasing. So this is called avalanche breakdown. This is called avalanche breakdown. So at sufficient high voltage, at sufficiently large voltage, this process occur, and this process will result in the enhancement in the current in the negative direction, and this is called avalanche diode. Avalanche diode is based on the avalanche process or avalanche mechanism. Avalanche mechanism occurs at very high voltage, At that voltage, few of the electrons will attain sufficient amount of energy so that while moving it collide with the covalent bond, and the covalent bond get broken, and this covalent bond again will generate two more electrons, and further this process will continue, but it is a slow process, but it will continue, and their time will come, their large number of electrons are generated in this region because of the covalent bond breaking. And again this, because these electrons which are generated now, so they will also attain a maximum amount of energy because of the applied voltage. So whatever electrons are getting generated, they will attain that energy, and they will again start generating another electron by breaking the covalent bond. And this is called avalanche breakdown, and this is called avalanche diode, and this is the reverse bias characteristics of your diode, and this is the reverse bias junction. So now if anyone asks you to draw the forward bias and reverse bias characteristics together, so you have to draw these IV characteristics in the reverse bias direction, and you have to draw the forward bias characteristics which has been discussed again previously. So this is the overall working of your PN junction under forward bias and under reverse bias, correct? In forward bias it will start increasing and the current is mainly due to majority carrier, and in the reverse bias the current is mainly due to the reverse saturation current or minority carrier. But at certainly very large amount of voltage, what happened, these minority carriers attain some energy, and while achieving this energy they will collide with the covalent bond. Similarly they will not generate break covalent bond here also, but they can break covalent bond anywhere into this region. Here also covalent bonds, so lots of covalent bonds are there, and these electron also moving very fast, so they will also generate some of the covalent bond, break covalent bond. So likewise large number of electrons are generated in this region, large number of electrons are generated in this region, they will cross the junction, and because of this current will increase, and this is called avalanche breakdown. Clear?